we heard your conversation broadcast here. Okay, so today I'm going to shift a little bit from what we've been covering mostly in the presentation so far. We've been talking about the numerics and how you refine and how you handle the resolved parts of the flow. But of course, in the atmosphere and the ocean, an awful lot of what happens is simply unresolvable by any methods that we're using, including refinement. It just happens over too wide of a range of scales. And so as we do this, we're increasingly moving from things that are fixed, where you might be able to select some parameters at when you set up the run, to something where you're dynamically adapting, either in space or in time, and therefore you'd like to have parameterizations that are aware of the resolution, that are modified as the resolution changes in comparison with the relevant physical quantities. And I'm going to be discussing a few examples today, and hopefully this will be a basis of kind of a second line of collaboration as a part of this Newton Institute program. My title talked about parameterizations in general. My examples are all from the ocean because I don't really know that much about the atmosphere, but I suspect that some of the characteristics carry over. Okay, so this is an example of two different models of the Southern Ocean that differ only in their resolution. And as you can see, these are just qualitatively different. One of them is a laminar flow. The other one is a rather turbulent flow. The one on the right corresponds much more nearly with what we think the real world looks like. The one on the left corresponds with what we're using for a lot of climate models. And so in this case, it seems perfectly natural that some of the parameterizations, for instance, of the baroclinic eddies that we used here, would simply be turned off and discarded. However, as we go to look at the whole world, the scale at which you would want to make that transition is probably something related to the first mode baroclinic deformation radius, i.e. the distance that a gravity wave travels before arrested by rotation. And what I have here is the ratio of the grid spacing in a 1 degree resolution global model to the deformation radius. The deformation radius gets smaller as you go to higher latitudes, even more rapidly than the resolution increases as a result of the convergence of the meridians and the use of a Mercator grid here. So that everything here that's kind of in this yellow and red range, the dominant scales of baroclinic instability are not resolved, and that flow is almost guaranteed to be largely laminar. Whereas in the range of the greens and the blues, you resolve that deformation radius well enough that you might have a turbulent flow if other conditions apply. And so in the case of this 1 degree model, you can see that over most of the domain, the flow is essentially laminar. However, there is a narrow equatorial band that's dynamically important where the scales of motion are in fact resolved, and you might have things like tropical instability waves. And so here you'd say, okay, let's just parameterize the effects of the mesoscale eddies everywhere. However, as we go to a somewhat higher resolution, this is 1/8 of a degree, something that's really quite computationally demanding and kind of pushing the envelope of what we can afford to do for climate. You can see that while we resolve the eddies over a wide range of scales, we still have a large portion of the ocean, and in fact, some oceanographically quite important places like the Nordic seas, where you simply don't resolve the eddies even there. Okay? So I think what we're facing is that even as we push to yet higher resolutions, we're still going to have some parts of the domain where we don't resolve the scales of motion, and so we're going to need to use adaptive and self-scaling parameterizations. This is with a fixed grid. Now you take and you apply these same ideas to something where you're refining your resolution, where interesting things happen, and because you're limited in your total number of degrees of freedom, you by definition are taking that resolution from somewhere else. So these same issues apply for adaptive grids, with the complication that you're going to have to be changing your parameterizations with time as you change local resolution. So a few considerations.
Ask a question about that slide.
Yes?
Often when you see the variable resolution ocean grids, they refine around the currents. But here, are you suggesting you should refine like the whole Antarctic, the whole ACC region should use higher resolution than the mid-latitudes?
If you scale it by the energy in the eddies, then you're drawn to the currents. But baroclinic instability is ubiquitous in the ocean. If you want to resolve it everywhere, then you have to put a lot of resolution into coastal areas where the the stratification is weak and the ocean is shallow.
And they show up as all the red in your...
And they're all the red, and they're everywhere.
But you should also refine the yellow region, too.
And you should also refine the Southern Ocean. The Southern Ocean is really important for climate and large-scale oceanographic questions. Yes. I mean, the challenge here is it's a little bit hard to say where you shouldn't refine, apart from, say, the tropical Pacific, and nothing like ENSO or anything interesting happens there. Okay. So a few considerations in designing the parameterizations. The first is we should do no harm. This Hippocratic principle is one that has been wildly violated by a number of widely used parameterizations in the past. So for instance, mixing in the horizontal in ocean models was discovered after about 20 or 25 years to be highly damaging to the water mass structure and completely changed the overturning circulation relative to any kind of theoretical or observational consideration. We should also pay attention to, if you're putting in closures for numerical reasons, you'd like them to be highly scale selective. You don't want what you're doing to clean up the grid scale to be too damaging to what you're doing to the parts that you're actually resolving. And the third principle that I think is worth paying attention to is anytime you have a dimensional constant that can't be directly related to some fundamental physical quantity or something you can measure in a lab, it's a clear indication that your theory is incomplete, that more work needs to be done. And this is unfortunately true of all too many parameterizations that we are using, where you have something like a diffusivity, an eddy diffusivity that you're not relating to anything else. It's just a number that you tune, a dimensional number. There are a few ways that you can approach developing appropriate parameterizations. The first one is if you think that you're putting it in for numerical reasons, tie the parameterization directly to your numerical limits. Tie it, for instance, to a cell Reynolds number when you get down to the grid scale. Wherever possible, if you have a partially resolved spectra, and you can therefore use what the model is telling you to kind of project what probably is happening over a complete range of scales, exploit that. Also, if you can come up with parameterizations that become self-regulating, it makes it a whole lot easier to run badly awry. So exploit that whenever possible. Use energy as a nice currency in some cases for determining how much mixing should go on by extracting the energy from what you actually resolve before applying it to doing mixing. And be aware, just kind of understand when there are qualitative phase changes, like with the eddies, the length scales at which you start to expect your model to behave qualitatively differently. Okay, so I have 4 case studies that I had prepared. Given that this is only a half-hour talk, I'm probably only going to talk about 2 of these, and the other 2 I can talk about in more detail later. The first one is the Laplacian and biharmonic Smagorinsky viscosities, and these are widely used. They've been used in some cases for 40 years, in other cases for quite a bit shorter. They illustrate some of the nice properties, and these are fairly mature by now. The others all have some degree or another of work that remains to be done. And so it's kind of more on these latter ones on the list, which I think would be fruitful grounds for collaboration in this Newton Institute program. Okay, so the Smagorinsky viscosity was first described in a paper by Joe Smagorinsky in 1963 that was never published, and finally described by Joe in the peer-reviewed literature in 1993, after this had become one of the more widely used parameterizations, both in the large-scale atmosphere and ocean modeling, but also for the LES community. And the idea here is that you would cast your viscosity in terms of a stress tensor, so it conserves angular momentum and has some other nice symmetric traceless tensor. And the elements of the diffusivities that are used, the viscosities that are used in this tensor, are going to be scaling with the rate of strain at the grid scale. So basically, for a solid body rotation or a uniform flow, they don't do anything. But here you're looking at the tension strain and the shearing strain. These are basically 2 strain rates. And they basically give you an estimate of a time scale that you're getting from the flows at the grid scale. So this has units of 1 over time. And then the length scale that you're using is something that's proportional to your grid spacing. So as your resolution increases, this viscosity decreases because you're starting to resolve some of the effects as you increasingly resolve those scales of motion. And what has been found is that in three-dimensional isotropic turbulence, this actually does a remarkably good job of parameterizing the downscale cascade of energy when you have a partially resolved spectrum, and for which there's a theoretical value of this Laplacian Smagorinsky viscosity. You could also use numerical arguments to argue for using something like this, where you want to make sure that by the time you get to the grid scale, that your viscosity is dominating your nonlinear terms, and this is usually expressed in terms of a cell Reynolds number. So if you define your near grid scale velocity variations after taking out solid body rotation and uniform flow and so on as u, then you get a sensible cell Reynolds number to be defined as in the usual way as u times your grid spacing over your viscosity. And with the Smagorinsky viscosity, the rate of strain scales with as u over the grid spacing. And when you've done the cancellations in the numerator and the denominator, what you're left with is that your cell Reynolds number is going to be equal to 1 over this non-dimensional constant. Okay? So for the 3D isotropic turbulence, the constant that you use here gives you a cell Reynolds number of 35. As it turns out, that's not terribly useful for large-scale ocean and atmospheric modeling, for the reason that when you have grid-scale variations of your tracer fields that are driven by the downscale cascade from your velocities, that leads to truncation errors. Anything happening at the grid scale is subject to truncation errors. And those truncation errors in the ocean can lead to mixing across density surfaces. Mixing that, in fact, is larger in some cases than the physical mixing across density surfaces. And so in order to control that numerically induced mixing, so these are two different test cases. This one is a three-dimensional eddying test case from a recent paper. From the same paper, this is a two-dimensional lock exchange test case. Basically, this is a measure of how much mixing is going on for strictly numerical reasons, and you'd like to be in the regime where your numerics aren't doing much mixing. And this suggests that for large-scale ocean models, you would like your cell Reynolds number to be something close to 1 in order to perform adequately. And this is something that has, in fact, been borne out in global ocean simulations. Okay, so the cell Reynolds number you'd like to use here is about 1 or 2. The one that you would get from the three-dimensional isotropic turbulence is 35, which is much too large. So that doesn't really save you without suppressing the eddy scales. Okay, and so the solution, perhaps, is to take the same ideas for scaling the viscosity and apply them, instead of to a Laplacian form, to a biharmonic, which is much more scale selective, less likely to do damage to the well-resolved scales. Scaling in the same way with the same time scale, but now going as the grid spacing to the 4th value, which then gives you an effective cell Reynolds number that's just 1 over the sum of these two constants if you have both Laplacian and biharmonic Smagorinsky viscosity. So this has the advantage that it's scale selective, that you set one sort of universal non-dimensional number. It applies for almost any flow. It's scale selective. It doesn't damage the things that are well resolved. The downsides here, there's no physical justification for this. It's just a numerical closure, but that's okay. You let the Laplacian do the physical part. You let the biharmonic clean up your numerics. The actual value you would set would be a function of your numerics. If you have, for instance, momentum advection schemes that are less prone to a downscale cascade, then you can scale this back. The only other issue here is that this can lead to a restrictive time step with highly anisotropic cells. And these have been fairly widely used in large-scale ocean and atmospheric modeling. These satisfy the considerations that I mentioned earlier. All of the parameters are non-dimensional and should be universal. You should just apply, set them, figure them out once, use them forever. They really don't do too much damage to the resolve scales. So this is kind of an example of a parameterization that works pretty well. Okay. Skipping over the second case study, we come to the diapicnal mixing that's driven by stratified shear instability. And I'm going to go through this very quickly in the interest of time. Basically, if you have a stratified flow with a shear, this tends to lead to Kelvin-Helmholtz instabilities, which in a kind of a fully statistically equilibrated case leads to vigorous turbulent mixing that you can characterize in terms of diapicnal diffusivity. And there are several options for parameterizing it. All of these parameterizations are aware of the local shear Richardson number. The reason this becomes resolution dependent is the shear Richardson number. Here is the stratification divided by the shear squared. Well, you have the problem that the spatial average of the shear squared is always larger than the square of the spatial average of the shear. Okay? And so when the mixing is subject to some function of the Richardson number like this, what this says is that if you fully resolved all of the scales, you should exhibit more mixing than you would diagnose just from the resolved scales. So this might be a good candidate for downscaling from resolved parts of the shear. The final case study is looking at baroclinic eddy restratification, which we do via interface height diffusion, also known as Jet-McWilliams diffusion in large-scale ocean models. And the test problem that I'm going to use to study this is a variant of the Phillips model of baroclinic instability. Now, this is a textbook model. It's easy. The math is simple. It turns into algebra in the vertical, so we know an awful lot about the peak growth rates, the longest and shortest scales at which you exhibit growth. In this case, I'm not interested in kind of a spin-down problem. Instead, I'm interested in kind of a statistical equilibrium. And so the way that we get that is we apply some damping of the zonal mean interface heights towards a reference value. So this doesn't suppress any of the eddies. It just means that you're continuing to restore the overall baroclinicity of the problem. And so the problem equilibrates before too long. In addition, we're applying a fairly strong bottom drag here in the lower layer to prevent the barotropization of the flow. In the real ocean, this would happen with rough topography. Eddies in the ocean don't tend to be big barotropic eddies. Instead, they tend to be surface trapped, but with fairly significant shear. And so this is putting us in a fairly oceanographic condition. The length scales at which the eddies kick in, the dominant length scale is something like 2 pi times the deformation radius. And the deformation radius here that I've chosen ranges as a function of latitude, mostly because of the changes in depth, but also because of the changes in the Coriolis parameter, from, say, 40 kilometers in the southern part to 20 kilometers in the north. Additionally, this is chosen to be baroclinically unstable, as evidenced by the reversals in the potential vorticity gradient in the lower layer. So this is kind of all of GFD1 course in about 2 minutes, captured in this one nice little simple problem. So as we let this problem go with just a little bit of noise, we find that after a few eddy growth timescales, we start to get this baroclinic instability at about the wavelength that you might have anticipated. And then over the course of the next few hundred days, you get this kind of equilibrated turbulent field. This is just one snapshot, but these things are just kind of rolling around all the time. And the effect of these eddies is to transport dense water equatorward and light water poleward. Okay? And so from a climate perspective, it's the heat transport that's the metric that you'd like to pay attention to. If you're looking at a different problem, you might have something else that you'd have in mind. So if we look at the upper layer flow at various resolutions at the same time, you see that in the very highly resolved scales that all of them are exhibiting this large-scale baroclinic instability. And although there are differences in details, the overall heat transport in these first 3 test cases is fairly similar. As you get to lower resolutions where you're becoming marginal in your resolution of your deformation radius, the eddy field drops off dramatically. And this is even more vividly evident if you look at the upper layer relative vorticity normalized by the Coriolis parameter. And so these three cases, they're doing the same things in terms of the overall heat transport, but you can see that there's still dramatic changes in the vorticity as you go to yet finer scales. Okay. So now if you say, okay, well, what is the overturning as a function of resolution? Well, that's this blue curve in here. The magenta lines are the RMS variability. I'm taking 5-day averages and averaging over a couple of years. The blue lines are some error bars where I'm estimating the number of actual independent realizations. But the point is here that out to resolutions of something like 10 kilometers or so, the eddies are qualitatively, they're essentially converged. As you get to coarser resolutions, the eddies become less effective and dropping off to the point where once you've no longer resolved the baroclinic instability at all, there's very little overturning. It's essentially a laminar flow in that case. And so somewhere between here and here, you're going to have to start parameterizing the effects of those eddies. So the way that we have traditionally done this in large-scale ocean models is with an interface height diffusion or a Gent-McWilliams viscosity that gives the same effect. The problem with that is that as we turn up this Laplacian diffusivity of the interface height, it's directly extracting available potential energy from the eddies as well as the large-scale flow. And so it actually suppresses the eddies before it attains the desired effect of parameterizing the overturning. So now this is a plot of the overturning transport as a function of the interface height diffusivity, the parameterized diffusivity that we're using. And you can see that whereas what we'd like is basically to capture the large-scale effects, the first thing that the eddies do, that this parameterization does, is it suppresses all the eddies. And only later does it contribute the diffusive transport. And you can see that here where the two pieces are broken out. The black line collapses well before the parameterized transport is able to get back up to the true solution here. And so this is an example, to paraphrase Winston Churchill, illustrating that interface height diffusivity, or Gent-McWilliams parameterization, is the worst of all possible parameterizations of eddy effects, apart from everything else we've tried. So we're kind of stuck with this as kind of the best thing available. But the worst thing you could do is to put in a bit of this and get yourself stuck in this kind of nether region where you don't have explicit eddies because you're suppressing them. You don't have enough with the parameterization because it's simply too weak. You want to do something where you're going to be jumping quite rapidly from one limit to the other as a function of your resolution, which suggests that perhaps what you should do is have a diffusivity that you use that's some function of the ratio of the deformation radius to your grid scale. And so you put this in as a modification to your diffusivity, and so maybe a reasonable choice would be something like this function, which starts off with 1 when your eddies are very badly resolved, and then rapidly drops down to 0 once you start to resolve the eddies. This is where we've gone from things that are fairly firm to this is wild speculation that this might actually work. Although I do know that the two end points, this should go to 0 here and 1 here. It's how it gets in between that's the subject for ongoing research. So this can then be applied to our large-scale ocean model. And so in the case of our 1 degree resolution, our scaling function here would really pick out just the tropics as where you're going to let the model tell you the full physics of what's going on. And outside of the tropics, you're going to be parameterizing it and hoping that you knew how to calculate that diffusivity. Whereas as you've gone to the much higher resolution, you're letting the model have free reign over most of the open ocean, most of the deep parts of the ocean, but still over the shelves or in the high latitudes, you're still saying, I don't resolve the eddies, I had better parameterize their effects. Okay. So now this is an idea that works pretty well, but we still have the diffusivity itself that we didn't know how to estimate. And so this is something that would seem to work pretty well with some ideas that various people, Karsten Eden and coworkers, or David Marshall and Alistair Adcroft have been working on, where you basically set up a separate equation for the unresolved mesoscale eddy kinetic energy. And this would have as its source terms the energy that your interface height diffusivity is extracting from the large scale, the resolved flow, plus perhaps something coming from bottom drag if you think that's a trigger for baroclinic instability. I think it probably isn't so much, which is why this number is tiny. And then you would have the energy lost somehow into the interior with a time scale, so that's a dimensional constant, i.e. I have failed. And then bottom drag, where I think I know what it probably looks like, and so this piece I haven't. And then you can take and use that to scale up your diffusivity to be some constant that you can maybe determine times a length scale that's either your grid spacing or the deformation radius times the velocity scale that you've diagnosed. And this becomes self-regulating in that the energy that this is extracting from the large-scale flow modifies, is extracted from the large-scale flow. As you modify the large-scale flow, you cut off the source of energy for this term. So this maybe becomes self-regulating with some desirable property. And so when we apply this, again with that resolution function in our 1-degree model and our 1/8 degree model, this is the eddy kinetic energy that we're diagnosing. And we're picking it out in similar places, although it's mostly places where the deformation radius is not so well resolved. So even in places like the Gulf Stream, we're only diagnosing the energy on the inshore side where, remember that resolution function said you don't resolve the scales. Whereas at 1-degree resolution, you're picking up this eddy energy basically throughout the ocean apart from the tropics. Then this can be used, again with the same resolution function, to calculate an interface height diffusivity. And the actual values here are probably a little bit weak, but the pattern here is quite striking in that we're picking up this term in the parts of the ocean where we know there to be fairly significant eddy variability. But by the time we've gone to an 1/8 of a degree resolution, we're basically not applying anything over most of the volume of the ocean. But in those places where the deformation radius becomes small, you don't resolve the scales, then you're turning it back on. And what this does is it allows you to take two different ocean models, completely different resolutions. And with this scaling, it's able to run quite sensibly, where the only thing where these two models differ is the resolution and the time step. And the time step mostly comes from a CFL number. So, I mean, the nice thing about this is kind of moving towards something where you don't have a whole bunch of things that you can tune. Everything is kind of self-tuning and aware of the state of the flow. And so this is something that I think could be pursued, although, as I've noted, there are a number of loose ends that have to be tied up. Dimensional constants that ought not to be dimensional, for instance. A shape that is not well defined. Oh, so this is just kind of summarizing things. Not so much for the purposes of people here in the room, but I know that this is something that's going to be shared. And so this, if you want to read it, it summarizes everything that I said. But I'm proposing that resolution-dependent self-scaling parameterizations like this would be a very good candidate to complement our work on developing adaptive and refined numerical techniques for the resolve part of the flow as a way of taking the physical parameterizations, making sure that the pieces that you will not be resolving are well applied, and taking the pieces that you are newly resolving and getting the parameterizations out of the way to avoid double counting or things like having the parameterizations actually suppress the scales that you should be resolving. So, thank you very much.
Thank you. Any questions? I can't believe it's not been done before. That's
Well,
not to be rude, but it's...
Which parts?
Well, the resolution-dependent scaling of the viscosity.
I am unaware of anybody who's done it before. We sort of do it implicitly, but not in a kind of a formal way.
It seems like the
It
thing
seems
that
obvious.
the essential thing to do.
I agree. Beth?
I'm imagining that when new architectures come online, there will be places in the ocean where we will be beyond the regimes of just, often now we talk about eddying versus non-eddying. It's been the big topic of the last 15 years. But in fact, one could go to scales small enough that you start resolving.
Some mesoscale eddies.
So those are still. I'm thinking about going into regimes where the flow isn't dominated by baroclinic instability. That in fact there are other instabilities that can in fact even dominate, such as where there's weak stratification, like the symmetric instability, right? So instead of converting potential to kinetic, you're converting kinetic to eddy kinetic. So you still get eddies, but it is not from the potential energy. And then you are opening yourself up to these parameterizations don't work. The release of potential energy, like GM, means nothing in this context. So I'm trying to think about, okay, this isn't going to happen tomorrow, but but it's with all of the variable resolution work going on. We've been talking about, what part of that will be interested to climate modelers or whoever, and moving into these other regimes where more physics is resolved is an interesting place. And these parameterizations, of course, these are the big ones. But it seems to me we should keep in our minds also that we could go beyond this debate of eddying versus non-eddying into some whole other regime in certain places, like along the shelves. Are you thinking about what to do about that? This is definitely step one.
Yeah, this is step one.
Yeah.
And I think we're going to learn from this. I think this will teach us a lot of useful lessons about how to get out of the way once you start to actually resolve it, and using your understanding of what's going on to really guide the.
Will help when the other
parameterization.
things come along. Yeah.
Right. You're going to have different considerations when you're looking at symmetric instabilities.
Right.
And we already are starting to deal with this with sub-mesoscale eddies, where right now we're in the case where we're so far from resolving the scales of the eddies, and yet their restratification effects are quite important, that we're having to project down the scales to try to get that the vertical restratification in the mixed layer. There will come a time when we start to say, okay, are we resolving the sub-mesoscale eddies, and therefore we should be getting that out of the way.
Exactly.
So I agree. And the beautiful thing about this is that this kind of long list of physical properties, that's job security for people who are actually thinking about what's going on in the ocean and working in consort with folks who are worrying about giving us great numerics.
Let's go and get some coffee. Thanks very much again.